Welcome to EPG Pathshala. In this module, we will continue our studies on sequence comparison, this time with multiple alignments. Now, what is a multiple alignment? A global multiple alignment with K is greater than 2 strings, that is, an alignment of more than 2 strings. Let's say I have a set of K strings, S1, S2, S3 going on to Sk. It is a natural generalization of the alignment of just 2 strings. So spaces are inserted into, within, or at either end of the K strings so that the resulting strings, they all have the same length, let's say L. The strings are arranged in, of course, K rows of L columns each, so that each character and space of each string is in a unique column. So this is an example. So here you have 3 strings, they are of different lengths. They have been arranged in such a way that spaces have been added into the strings so that the total length becomes the same. Now, as you can see out here, so while doing this, care has been taken that maximum matching between the different strings are also achieved. And that is the purpose of multiple alignment. So mathematically, we will define a multiple alignment as an alignment of K strings S1 to Sk in such a way that the aligned length of S1, let's call it S1 prime, and it becomes equal to the aligned length of S2 and so on and so forth until it becomes equal to the aligned length of Sk. So when you do this, this is the common view of a multiple alignment. It is common to set up these boxes where the characters are supposedly equal or sometimes similar. Now, as in this case, one has become a little bit over enthusiastic with the boxing, I should say, and the amino acids are not even very similar to each other. They have been boxed together. There is no really any scientific basis on how you are putting these boxes. Some people put them for the characters which are exactly equal. Some people put it when they are similar. Some people consider it a very generous criteria for similarity. I would suggest that while you can use your own criteria, it is better to be a little bit strict, because in that case only the most important features of the multiple alignment gets highlighted. So understanding multiple alignment, of course, we have these problems of terminology. A common term that comes in is homology. Now, what is homology? Homology is a similarity between, let's say, 2 protein or gene sequences that is derived from a common ancestor. Identification of homology is central to the analysis of phylogenetic analysis and evolution. Now, it's a very common mistake when students talk about 20% homology or 30% homology. Now, it's incorrect to say so, since homology simply means that I have a sequence S and a sequence T and they share a common ancestor. There cannot be percentage homology, so you can't have a percentage common ancestor. So of course you can say given a sequence S and a sequence T are 20% similar. That has a meaning. But sequences are either homologous or they are not. There is nothing like 20%, 50% or 90% homology. The second term which we have to understand is alignment itself. What is an alignment? Computer science would say it's a matching between strings such that their lengths are equal and so on and so forth. In case of biology though, one way to look at it in alignment, that it is a hypothesis of positional homology between the bases or amino acids contained in 2 different sequences taken from 2 different sources. And that has important consequences in many areas, including evolution, structural biology, functional areas like genomics, and so on and so forth. So the goal of multiple alignment is to generate a concise, information-rich summary of sequence data. This can be used to illustrate similarities and differences among a group of sequences and by extension a group of organisms. Alignments are often used, in fact, as models for testing different evolutionary hypotheses, so on and so forth. Now, when you are constructing a multiple alignment, the general identity between the sequences which you are going to align becomes very important. Now, if this identity is, let's say, greater than 80% or so, then you can use any program to do your alignment. Automatically, under default settings, you will get the right answer. If, on the other hand, your sequence identities in the sequences in the alignment are somewhere in the 40 to 60, it may be a good idea to use more than one method, and there are a number of methods of doing multiple alignment. Number of programs are available to do your alignment, and pick up that alignment which is generally returned by a number of programs, because many of them, they may not agree with each other. So some of them will not agree with the others. Hopefully most of them will agree. If your sequence identities fall in the range of, let's say, 10% to 30%, that's quite a risky zone to get a good alignment. One uses advanced techniques, profile HMMs and so many other things, for example, which can, even in such cases, provide you a reasonably correct alignment. But that's something which is better left to be done by the experts. And then if your sequence identity is even 0 to 10%, and very, very low sequence identity, in such case, you will definitely require a lot of structural information, and those kind of alignments are really very difficult to construct, and it's really very difficult to be sure that the alignment is actually correct and making biological sense. So this zone between 0 to 10%, we call it midnight zone. Nobody knows what we are doing, whether we are doing things correct or not. Between 10 and say 30, we call the twilight zone. We have certain ideas that maybe we are on the right track, but we don't have enough information. Between, let's say, 30, 35, all the way up, it's a daylight zone. You are absolutely sure what you are doing. You cannot go wrong. So please note that when constructing a multiple alignment, take a look at the average sequence identity between pairs of sequences. If they are very low, be very, very careful of what you are doing. So, how does one construct multiple alignment? Now, having learned about our two sequence alignment methods in the previous module, one would think that, oh, I could use probably a dynamic programming technique like Needleman-Wunsch or Smith-Waterman to do that. So let's think about it. So if I have R sequences, for example, I could think about the table, dynamic programming table, which we constructed while doing Needleman-Wunsch, would have now R dimensional hypercube. Now, just when you have just two sequences, it's a flat plane. You have x-axis and y-axis, we make the table. If you have three sequences, it becomes shaped like a cube. If you have R sequence, you have a R dimensional hypercube. And one can do that. In principle, that's quite doable, and it is shown in the next slide. Next slide, please. With three sequences, so now your table is now in the shape of a cube, and the best alignment is a walk which is going through the middle of the cube, shown by the dark line over there. Yes, it is quite possible. But the trouble with this approach is the algorithmic complexity of the process. As we had seen for two sequence alignment, both the time and the space complexity in the general case is OMN. It is the product of the length of the two sequences. Now if you have R such sequences, let's say M, N, P, Q, R, so on and so forth, it will be the product of the lengths of all of them. and that number very rapidly becomes astronomically large. So whatever be your computing abilities, aligning more than 3-4 sequences using a dynamic programming technique would require not days or months, but maybe years or centuries of continuously running computers. Clearly, dynamic programming is not a possible solution. So while in principle one could use the dynamic programming technique to align any number of sequences, but there is a little problem. As we had seen in the previous section on two-sequence alignment, that the time complexity of aligning just two sequences is proportional to the product of the lengths of the two sequences. If m is the length of one and n is the length of the other, the time complexity is proportional to m times n. Now let us say I have 5-6 sequences of length m, n, p, q, r. So what would be the time complexity? Now it would be the product of all of them, m times n times p times q times r. Now, even for reasonably sized sequence length, say 100, 200 amino acids, when you are multiplying all of them, the product becomes very soon astronomically large, which means that the time taken to construct this alignment also becomes astronomically large. Regardless of whatever computers you can do, the time can easily go on, not from months or years, but even to centuries. Clearly, therefore, using dynamic programming techniques for multiple alignment is not a good idea if you have anything more than 3 sequences. So we have to look for some other different methods. Now, one of the techniques of constructing multiple alignment is a method called minimizing the sum of pairs objective function. Now what is this? Ideally, the sum of pairs function is that you have your, say, n sequences, you take them pairwise, every possible pair. So if you have n sequences, you have n times n minus 1 divided by 2 pairs. Each pair, suppose a 2-sequence alignment was done and the best alignment score was obtained, say S is that alignment. The sum of that would be the best possible alignment that you can get. Sum of all the pairs, scores of all the pairs that you can make would obviously be the highest possible solution, the score that you can get. So the idea is like this, that of course we cannot find that out in any direct approach, but whatever we do, we insert gaps and spaces anywhere and everywhere in the sequence, but keeping an eye that this sum of pairs score is becomes maximum if we are using a score, or becomes the minimum if we are using a penalty function. This is illustrated out here. Here I have 3 sequences. The sequence 1 and the sequence 2, they align with a score of 4. Sequence 2 and sequence 3 aligns with a score of 5, and 1 aligns with 3 again with a score of 5. Now the best alignment here has a score of 14, so which is the sum of the score of every pair. So again, do whatever you like, but try to obtain the largest score. Now what actually you do? Now it can be shown that whenever you are doing sum of pairs alignments, it's equivalent to something called the center star method, which is to say, you take one sequence and pick another sequence at random from the set of the remaining one and you align them. Then you pick a third again at random and you align with the first two, and so on and so on. So each time you're aligning, you can add spaces either to the newly added sequence or to every other sequence which is there previously that you have had. That's all you have to do. So the best alignment would be found. Now of course you can do this in different orders. You can pick up the sequence in any order you like. The best alignment would be for a certain particular ordering, and that is the one which you have to find. The trouble with this method is that if you have a large number of sequences, there are a very large number of orders or permutations of that sequence. So therefore, while this technique is good, but it becomes quite difficult to implement in real life cases. Another approach of doing it in fact currently perhaps the most popular approach which is being followed, was first proposed by Feng and Doolittle in 1987. What they do is they try to build an evolutionary tree from the sequence data while simultaneously constructing a multiple alignment. So something like the way the center star alignment goes in, but instead of picking up sequences in arbitrary order, they pick up sequences based on a certain logic and based on an evolutionary tree. There are many programs which implemented their idea, and one of the programs called Cluster W, written by Des Higgins, is perhaps currently has more than 80% market share of this alignment, multiple alignment programming technique. So let us take Cluster W and go through how it does and follows its progressive alignment method. So what it does, first given n sequences, it aligns them pairwise, right? That is what you do, n times n minus 1 pairs, and you can create out of n sequences, and you align them pairwise. Now given this alignment, you try to create a matrix where you have the alignment score of each sequence with all the others. Now this let us call the distance matrix. Now given a distance matrix, you can create what is known as a neighbor joining guide tree from these alignments. This guide tree will give you the order in which the progressive alignment will be carried out. So this guide tree is constructed like this, that that pair of sequence which has the highest score or which is the most closely related, align them first, and then this alignment is considered fixed and will not be changed. If a gap will have to be introduced subsequently, then it will be introduced in all the sequences, that's in both the sequences of the pair exactly at the same position, so that their relative alignment does not change. Then you can add onto sequences the one which is the most close to these two. Now that may be a single sequence, or that may be something already in another alignment. And how do you handle these? So these you align and you progressively build up this alignment until you have exhausted all the sequences that you have in your set. So let's illustrate this. So let's say I have 5 sequences out here, and at the top left of the figure I show you the distance matrix, which are the alignment scores of the one sequence with the other. So for 5 sequence I have 10 such distances in the matrix, as you can see, 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10 numbers are there in the table on the top left. Now having done that, what we clearly see that the hemoglobin of human and hemoglobin of horse, these two are the most similar, right? And between them they have a distance of only 0.13, so we align them first, right? So this is for the A chains, and then we also find that the B chain hemoglobin of human and horse are also very similar, so we align them also together. Having done this, we can combine these two alignments in the third stage. So we have all the hemoglobin alignments, and at the last stage we take the other protein, myoglobin from whale, which is very different from the remaining 4, is now aligned in the last step. Now while aligning, let's say when I am aligning the hemoglobin A chain from human and horse with the hemoglobin B chain from human and horse, and a gap needs to be inserted somewhere in the A chains. Now if the gap is inserted at a particular position, it will be inserted both for the A chain of the horse and at the human simultaneously in the same place, which is another way of saying that the local and the alignment between human A chain of horse and human, which have been made once, that will not change regardless of any insertion of gaps, because gaps if are inserted will be inserted in both places. Now there are many advantages of this technique, the most important one being its speed is really very rapid. It has a few disadvantages, if we can call them. It doesn't have an objective function, so you do not know how good is an alignment. You know if it is there, you get something, but whether it is You can even do better, you have no way. And of course, there is no way of telling that if the alignment is correct. Now, what do I mean by correct? It's not very clear whether the alignment is biologically correct or not. That is difficult to be said. And of course, there is the so-called local minimum problem, that while doing progressive alignment, if an error happens by some means, an error happens early in the alignment process, then that becomes fixed and it cannot be corrected. So everything goes wrong. So that sort of a minor disadvantages are there. Nevertheless, cluster W remains perhaps the major program for doing multiple alignments at the present time. So let's take an example. So here are some, let's say, call them protein sequences, but I think we can see some English meaning for them. So if we align them, these three, glycine, alanine, arginine, phenylalanine, isoleucine, glutamic acid, leucine and aspartic acid constituting the first part, and not Garfield the cat. So if you align them using cluster, then what happens? Well, for the most part it works. Garfield matches with Garfield, fine. The matches with the. But last matching with fast is alright perhaps. But look at the third sequence, very fast, very should have been an insertion. But there is a little bit error. So fast has that moved away. And similarly in the fourth one, fat is not the same thing as fast. So it could have been anywhere. But again, it has been connected to fast. So if we look at this kind of alignments, the first and the second, more or less the first part of the things, so the Garfield, the last and fast, etc. have aligned very well. But there's a little bit of a problem. Sometimes cat gets aligned with fat, sometimes fast gets aligned with fat. So the same situation is there. If you look at multiple alignments, they work very well using done by cluster. They work very well in some places, but there are certain errors. Sometimes some certain errors can creep up in certain regions of the alignment. So if one looks at this kind of multiple alignment, that in some occasions, some situations, in some parts of the alignment, some errors can creep in. It's always a good idea to manually check your alignment, and sometimes you can correct it pretty easily with any editing Microsoft Word or whatever you have. You can correct it manually, and that's always a good thing. Do not just trust an alignment, whatever the machine gives you, particularly if your sequence identities are not very high. If you look at this, the last one, the fat cat, that is the one which is not really very poorly aligned, and that's the one which is different from the rest. So particularly for those sequences which are rather different, there you need to check your multiple alignment rather carefully. Now you can align protein sequences, you can align DNA sequences. Sometimes you can translate a DNA sequence into protein, you can align them. The question always comes in, is there any difference between taking a gene and aligning the DNA sequences and translating them into protein and aligning them? Theoretically, there should not be any. That's what should be the expectation. But think about it this way. There are only 4 letters in the DNA alphabet. So the probability that randomly, without any biological significance, 2 letters are matching has a probability of 1/4. Now if you do that in the protein space, there are 20 amino acids. So the probability that there is a random match in a protein sequence space is 1/20. As a result of this, protein sequence alignments are much less noisy than DNA alignments. There are chance misalignments in DNA have a 5 times greater probability than in case of protein sequences. So it is always a good idea to translate your DNA sequences into proteins, whether they code or they don't code, does not matter. Translate them anyway and align them in protein space. If you want to construct a DNA alignment, once you have the protein alignment, then reverse translate the protein sequences back to DNA and construct your DNA alignments. It's not a good idea to align DNA or RNA sequences directly. One thing about aligning is that as I've been talking all along, that you have a score for an alignment. Now how do you assign that score? Right? Now there are many ideas about how scoring systems have to be made. The simple thing is that I have a sequence identity, that if I have two amino acids are same, I give it a score, let's say 1. If they are not the same, I give it 0, right? Substitutions, indels are all 0, and if there is a match, I have 1. Well, that can be one example, but there are other examples as well. So one could think about related amino acids getting a higher score. For example, valine and isoleucine are both very hydrophobic and are generally very similar. So if a valine gets replaced by isoleucine, I give it a little bit higher than if valine is replaced by, let's say, aspartic acid. That sort of thing, that you have a concept of relatedness in terms of structural, physicochemical, whatever other parameters, and you can use. Question of course comes on what sort of parameters you are going to use, and there can be some arbitrariness over there. Another idea is that due to Margaret Dayhoff and her co-workers, now she thought that okay, if I know that if I have two proteins which are homologous and which are perfectly aligned, but of course there are a few substitutions here and there, then what are the substitutions? If I know that, are they all completely random, or there are some preferred substitutions? If there is any preferred substitutions, I can construct a scoring thing out of that, just the probability of a substitution preference. Well, that's a good idea, but it creates a chicken and egg problem. To obtain the substitution probabilities between different pairs of amino acids, for example, you need to first have a perfect alignment. But in order to get a perfect alignment, you need a substitution matrix. So how do you do this? Dayhoff solved the problem. Now of course one can just say 1 for identity and 0 for not identity, but that's not the only way to do this. One could think of that if two amino acids are matching, fine. If they do not match, we consider how different they are. For example, valine and isoleucine are two similar amino acids, usually occur in the same places in proteins. So one would think that okay, replacement of a valine by isoleucine should have a higher probability than replacing the valine with, let's say, glutamic acid. Now you can choose whatever parameters of similarity between amino acids which you want, maybe structural, maybe their size, maybe their physicochemical properties like hydrophobicity, charge, or what have you. And based on that similarity, you can create a substitution table. That's fine. That's one way of going about it. Another way was thought of by Margaret Dayhoff and co-workers. Said, okay, if we consider one protein from one organism and a homologous protein from another organism, and we align them together, and then we see how many times one amino acid is changing into another one, I will get a substitution preference from that, and from that I can construct the probabilities of mutating one amino acid in one protein to another amino acid in a homologous protein. So in this way one can construct a scoring matrix, but to do that one would have to find out the likelihood that the alignments columns are drawn from the population of correct columns as compared to the likelihood that they are generated by chance. Luckily, there exists independent and reliable methods of deciding whether a particular scoring a matrix makes good results. So because the frequency by which that a column X over Y appears in a correct alignment depends on the evolutionary distance. So in other words, if we have two protein sequences which are not evolutionarily different, in that case they will have very few substitutions in indels, and the number of substitutions will increase as the sequences they diverge in evolutionary time. So one therefore can use this sort of a function, that S equals log of the probability that amino acid X changes to amino acid Y but one has to normalize this by using the probability Qx and Qy of the existence of the amino acids X and Y. Now this, of course, the log term is used because all these P's and the Q's are probabilities numbers. They are between 0 and 1, so that the ratio becomes rather inconvenient. So using a log term makes it quite convenient. This one is called the log odds score. So what Dayhoff did, she constructed a log odds probability matrix, something which she called the point accepted mutation or percept accepted mutation matrix, from a set of perfectly aligned proteins. But wait, there is a problem out here. To get a set of perfectly aligned proteins, you need a very good scoring matrix. And to get the scoring matrix, you need a set of perfectly aligned proteins. So how does this happen? So what Dayhoff did is that she picked up proteins which are very, very similar. More than 85% of the proteins, the amino acids in these pairs of proteins were identical. Now once they are that kind of similar, as we had seen before, that when the sequence similarity is very high, just put them one below the other and they are aligned. So using such alignments, she looked at the few differences that they are there, and from there she calculated the probabilities that amino acid X changes to amino acid Y and constructed her log odds matrix. Now another way to look at it is that once the proteins from which this matrix has been created, they are very similar, so very little time has passed in their evolution. So that matrix one could consider as a unit of evolutionary time, that about just 1% change has just about happened. So one can now in principle calculate the probabilities of substitution of one amino acid into the another one if I have a perfect alignment already. But wait a minute, the problem is this, that in order to construct the perfect alignment, I need to know the probabilities of substitutions. And I want to calculate my probability of substitution from a perfect alignment. So I have a chicken and egg problem, how to do it. What Dayhoff did is that she took a set of sequences which were more than 85% identical. And in such cases, you just put one below the other, one sequence below the other, and you get a perfect alignment. From there, she calculated the differences. That what is the probability that a given amino acid changes to another amino acid, a given amino acid X changes to another amino acid Y. This was normalized in such a way that these probabilities are true only about 1% of the protein sequence has changed its character, and therefore this was called percent accepted mutation matrix, or PAM matrix, or PAM1 matrix, because 1% had changed. Now one can think of PAM1 as a measure of evolutionary time, that is the time taken just to have 1% change in the protein sequences. Now having done that with this PAM1, which was derived by inspecting the frequency of amino acid substitutions in aligned sequences with at least 85% identity, one gets the relative frequencies and one can construct this log odds matrix. Now while this is perfectly fine, this cannot be used to align any arbitrary pairs of proteins, because they would have much larger divergences. Remember, this matrix was created specifically with a set of proteins which were more than 85% identical. So what does one do for proteins which are, maybe 20%, 30% or 40% identical? Clearly, the PAM1 matrix is not very suitable in that case. What does one do there? Now, while PAM1 matrix is perfectly fine if two proteins are very, very highly similar, they should not really work if the proteins which we are comparing, they do not have more than 85% identity. However, there is a way out. So let us consider a PAM2. That is, if 1% mutation happens in PAM1 time, what would happen in PAM2? Maybe 2%. So if then amino acid X changes to Y in say PAM1 and then changes to Z in another PAM1, So I would like to know what is the probability that an amino acid has changed from X to Z. Now think about it. Now when you are looking at the protein, you don't know what has happened in between. You just know 2 palm units have passed. So X may have changed to Y, Y may have changed to Z. But X may also would have changed to A, and A would have changed to Z. Now if the probability of X changing to Y is, let's say, Pxy, and Y changing to Z is Pxz, the probability that X changes to Z by this pathway is Pxy and Pyz. But if X changes to A and A changes to Z, then the probability that X changes to Z by the way of amino acid A would be Pxa times Paz. Now clearly, while coming from X to Z, it can come through any one of the 20 amino acids. So you have separate pairs of products of probabilities which you have to add up, and thus you have the formula out here that if R2 X to Y is the probability that amino acid X changes to amino acid Y, it is the sum of the products that amino acid X changes to any of the amino acid Z, and then amino acid Z changes to Y, where Z can be each of the 20 amino acids. If you look at this formula, anybody with maybe 12th class maths background says this is the formula for matrix multiplication. So what does one do therefore? To construct PAM2, I simply take matrix, the PAM1 matrix, multiply by itself, I get PAM2. This way one continues, one can make PAM3, PAM4, PAM10, PAM100, PAM200, PAM250, or whatever you like. In practice, one finds that like something like the PAM250 matrix is pretty good at detecting protein sequences which are homologous but are so far away, that millions of years of evolution has passed and as many changes as possible has happened. So in general we prefer to use the PAM250 matrix. However, if for some reason we are working with protein sets which are very, very similar, we would probably like to use PAM15 or PAM30 or whatever matrix is possible. So here is an example of the PAM matrices where, as you can notice, alanine with alanine, so no change there, has a score of 2. Arginine with arginine has a score of 6. What does it mean? That in general, alanines are more variable. So if in some case alanine does not change to anything, you don't get a big penalty score for that. But arginines, whenever they are there, generally tend to be much more conserved. So if an arginine is replaced, there is a big weight penalty, it has to be paid. So when an arginine matches another arginine, a larger score. The polar and large and polar arginine amino acid is very little likely that it is going to change with a small and hydrophobic alanine. So therefore the penalty for arginine and alanine is rather low, it's negative, -2. So this way, this entire matrix has been constructed and is the common one which is used for aligning proteins. Now that's not the only way. One difficulty which many people say about the PAM matrices is that, wait a bit, you actually calculate PAM1 from real observations of protein sequences and the rest of it is just extrapolation. Now let us say that you make a very small error somewhere in computing PAM1. When you compute PAM2 out of PAM1, this error is going to get multiplied. And when you go on and on and on and on up to PAM250, for example, any errors that you make in making your matrix, they really get multiplied. So such things which are extrapolated is not a very good idea. So another way out was found by Henikoff and Henikoff, who created what is called the block substitution matrix. Now before doing that, they created a blocks database, which is a huge database of completely ungapped multiple alignment of hundreds of protein families of different levels of sequence identities. Now in such cases, once you have such an alignment, and by the time the blocks database was made, huge number of sequences were there in the data banks, so constructing them was not a problem. So the substitution probability is simply counted off by seeing the number of times amino acid X has changed to amino acid Y for a given level of sequence identities in the proteins, and that's how the block substitution matrix or BLOSUM was created. In principle, BLOSUM operates just like PALM. Turns out the BLOSUM 62 matrix, which was generated from alignments where the sequences have a minimum of 62% identity, they works best. Now only one thing, there's a little bit confusing terminology between BLOSUM and PALM, that for PALM, when PALM1 or PALM2 is supposed to be used for sequences which are very similar, well, PALM250 is used for sequences which are rather different. In case of BLOSUM, it's the other way. BLOSUM1 and BLOSUM2 or BLOSUM10 is used for sequences which have only 2 or 10% identity, which means very different sequences. While BLOSUM 62 or BLOSUM 89 or BLOSUM 100, these are used for sequences, or not really 100, BLOSUM 90 maybe, are used for sequences which are 82 or 90% similar to each other. So higher numbers for more sequence similarity in case of BLOSUM, while higher numbers for less sequence similarity in case of PALM. So with this, let us summarize what we have learned. We tried to extend our knowledge of two sequence comparisons in trying to do simultaneous comparisons of multiple sequences. And very early on, we could see that the techniques of two sequence comparisons, whether Needleman-Wunsch or Smith-Waterman, is not going to work if you have more than 3, 4 or 5 sequences. It becomes horrendously slow and difficult to do. So different other techniques are invented. One of them is the sum of pairs objective function minimization method, sometimes also called the center star method, in which one picks up sequences one by one and constructs an alignment, and essentially the problem is to find the right order in which to do it. The other approach is called the progressive alignment technique, which in principle is similar to center star in that alignments are constructed one by one. However, the order in which they are to be aligned is suggested by a preliminarily or a previously constructed phylogenetic tree. Currently, the popularity of the progressive alignment method is very large. And then we also spoke about scoring matrices. That is, whenever you are constructing an alignment, when you are grading it, how similar it is, you have to assign a score. How do you construct a scoring alignment? Essentially, the idea which is most followed is that you find out the substitution probability that an amino acid X changes to amino acid Y in a certain evolutionary time, and using that probabilities you can create a substitution matrix, which is done. There are two classes, PALM and BLOSUM, of substitution matrix. In case of PALM, they also come with a number, PALM1, PALM10, PALM100, PALM250. If the number is small, they are to be used for alignments which are very, very similar. If the number is large, they are going to be used for alignments for sequences which are very different. In case of BLOSUM, it goes the other way. BLOSUM, larger number, the sequences are very, very similar. BLOSUM followed by a small number, the sequences are very different. Thank you very much.